Hello, welcome back. This is the first lecture about amplitude amplification, that is a very important quantum computing primitives. We're going to look at two pieces of the amplitude amplification quantum primitives. One piece is the flip operation that we already seen briefly in another lecture, and then the piece about the mirror/groover. Amplitude amplification is a very important tool that converts phase difference in our quantum state that are not accessible by reading operation into readable magnitude differences. Readable means that we can measure and see the differences. In the literature and the textbook, together with amplitude amplification, that is a commonly used term, we can find also the average and diffusion quantum primitives. Bear in mind that there are also other terms describing these quantum primitives that we're going to call here amplitude amplification. This slide contains a motivational example. So we have three quantum register A, B, and C of 4 qubits. So we can encode 16 quantum state. And then you note that these quantum register, they have the same magnitude, but they have one of the state where the relative phase has been flipped. So in this case, we have the quantum state 1 with the phase that is flipped. In this case, we have the quantum state 3 with the relative phase flip. And in this last case, register C, we have the state number 12 that has the relative phase flip. Obviously, if you're going to measure this different configuration, all these different states will be equally probable. So all these states will have the same probability of being a measurement. And the measurement also will destroy all the phase information. So the relative phase will be completely unavailable. So what we want to do through the amplitude amplification is to transform this relative phase difference. For instance, we have encoded here a relative phase in 1, here in 3, and here in 12 state. What we're going to do, we're going to transform this difference in relative phase in a difference of magnitude. So the amplitude amplification primitives allow to go from here to here. In this case, for instance, if you do a measurement on the quantum register A, we will measure 1 as the most likely state. In this case, number 3 as the most likely state. In this case, number 12 as the most likely state. So we go from a situation where we cannot distinguish through the measurement our mark or flipped Q state to a situation that we can actually measure and observe that state that we have been flipped. The first primitive or piece of amplitude amplification is the so-called flip primitives. So to mark the qubit, we use a circuit that takes our register initially in the state 0 and mark one of its value. So in this case, we want to mark with the change of the relative phase. We saw this briefly when we talk about conditional logic and phase encoding. You see here, for instance, we prepare our quantum register in equally likely superposition of state, and then we flip, we mark a qubit by using this flip operation. This flip operation is hard-coded, so there are different quantum circuit to provide different flipping of different qubit state. So this particular case here, this quantum circuit allows us to flip the quantum state 3. This particular case allows to flip the state 0, and this multi-CZ quantum circuit allowed to flip this last state, number 15. So we see that we want to basically mark with a flip of the relative phase one of the state, and we can use one of these quantum circuit to flip it. After we apply the flip operation, so that means that we change the relative phase, we rotate by 180 the relative phase. what we do, we have a primitive that change the flip, the relative phase in a difference of the magnitude. This primitive to change the difference in the relative phase into a difference in the magnitude of the state is called mirror primitives, and has basically Hadamard gate for each qubits, and then he has a NOT operation, he has a multi-control CZ, and then again a NOT operation and Hadamard gates. The mirror operation is commonly called the Gruver iteration in quantum computing literature, from the person who invented Love Gruver. You might have also heard about the Gruver's algorithm for a search of an unstructured database, and was the first algorithm implementing this flip mirror routine. The amplitude amplification primitive is just a generalization of the Gruver's original algorithms. We'll see one of the applications will be to change the flip to a conditional flip that will allow us to look for particular value in a structured database. We saw in the previous slides that through the amplitude amplification we can transform a flipped in the state into a difference in the magnitude, like this. So we see that the magnitude now, they are within each state are now different, and the performing read on the QPU register A, B, and C is very likely, although not certain, to reveal which value had its phase flipped. So we can also calculate the probability of finding the mark value. The mark value now, after the amplitude amplification iteration, has a read probability of roughly 50%, so 47.3%. So approximately half of the times we will measure the state that has been flipped. So the known mark value have a probability of 3.5. So this gives us almost 50% chance to obtaining the values that has this phase to flip. So note that the mark phase has now the same phase as the rest of the register. So we cannot apply this trick, right? So you see the phase is now the same one of all other states in the quantum register. Phase here is now flip, and phase here is now flip. This is the last slide, and talk to you soon.